Alright, so when we do an antiderivative, we want to remember that the derivative of the natural log of u is equal to, well, u prime over u. Or in other words, du over u. Therefore, the antiderivative of du over u is, you realize that the derivative and antiderivative are basically just inverses, natural log of u plus some constant. So that's the main thing here. If you get something to look like this, you're going to have a natural log. Now, when we're talking about powers, it really is like if you have a power 1 here and a power 0 here, you're probably going to talk about a natural log. Power 2, power 1, you're probably thinking about natural log. Now, that's something else entirely. But over here, I see 2 and 1, so I want to think natural log. But you really have to have it in the exact right form. So let's let u equal the 3x plus 2. We're going to do a u substitution, so du equals 3 dx. And there's the dx, but I don't have the 3, so I can solve for dx, dividing over the 3. And let's rewrite the equation. Okay, so dx is going to be du over 3. And in the bottom here, I've got this, which is my u. Okay, so I got 1/3 integral of du over u. You don't have to pull the 1/3 out, but you can realize that this part is totally separate. So this is our new rule. The antiderivative of du over u is natural log of u. So I have 1/3 ln of u, which is the 3x plus 2. And there's a quick note here. The natural log has to be defined for only positive numbers. It can't even be 0. Natural log of 0 is undefined. There's nothing to say that x has to be positive over here. So whenever you do a natural log, you actually need to put the absolute values on them. Whenever you're doing the antiderivative that results in natural log, that being said. Now, if it's x squared plus 2, that's positive, and so you'll see the book dropping their absolute values when they don't need them. But I would err on the side of caution and just put them in. All right, let's try here number 9. Number 8 will be very, very similar. You just do your substitution. Let u be the bottom, and there's your du. Off by a factor of 2. Let's try 9 together. Now, you'll notice the formula, u's on the bottom and du's on the top. It kind of has to be that for this type of problem. So if we let u equal tangent of x, then du, which we learned a couple minutes ago, is really just secant of x. Secant squared x, sorry. So then the numerator is secant squared x dx, that's our du, and tangent of x is u. So this would be natural log of, well, u, which is tangent of x. And since tangent can take on positive and negative values, we definitely need the absolute value. We always need a plus c. Okay. Let's try this next one here. Now in this case, it's a little bit tricky to kind of tell what you want to do right off the bat. So usually when you do u substitution, you let u be the kind of complicated part. So if we let u equal the x plus 1, du is just dx. Alright, that doesn't cancel out the 2x. So let's see what we got here at the bottom. We got 2x over u squared, and then du is equal to dx. Can't have two different variables, so anytime we have this situation where the x doesn't cancel out, we try to solve x for u. So x is going to be u minus 1. And we can plug that in for x. Okay. Well, first this doesn't seem to help. We end up having that plus 1 on the bottom turn to minus 1 on the top. But it actually does help. 2u minus 2 over u squared. And now I can break this up into two separate integrals. Both have the u. I have the integral of 2 over u minus 2 over u squared. First part's a natural log. So we have 2 ln of u. And the other part, this is really just minus 2u to the negative 2. This u to the negative 1 part is the only thing that gets to the natural log. This is not a natural log. This is just power rule. We add 1 to it, so this will be u to the negative 1. And then we divide by negative 1, making it a positive 2. Plus c. And the last thing is to rewrite this with our u's, plug back in, and we're running out of space at the bottom, so I'm going to put this up here where I have nice, lots of space. So 2 ln of u, which is x plus 1, my absolute values on it, minus 2 is that u to negative 1, so over x plus 1 plus c. And then we get our final answer. Always check it by taking the derivative. Alright, last thing we're going to talk about, I'll show you one really quick, is anytime the numerator is bigger than the denominator, you're going to use long division. So if you don't know long division too well, then you can watch a video I have on long division. But the top always goes inside, the bottom comes outside. And then you say, what do you multiply x squared by to get to x squared? That's 1. Then you distribute out here. X squared plus 1. And you subtract the 2 lines, and you're left with just regular old x. This does not go into it, so it's plus x over x squared plus 1. And that's what this really is. It's equal to the numerator up here. So we got the integral of 1 plus x over x squared plus 1. And we can do both integrals totally separately. So on the first one, the antiderivative 1 is just x. And the second one, if you set u equal to x squared plus 1, then you get du to be the 2x dx. Well, we have to still take this 2 and divide it out so that we can get just the, the x dx. So divided by 2, this ends up being x dx is du over 2u. And you see how I didn't really even do the antiderivative yet. So I can do this as 2 separate integrals entirely. So from here, the x is just x plus 1/2 ln of the u, which is x squared plus 1. Now you notice I didn't put the absolute values on there because x squared is positive plus 1 is a positive. But it doesn't hurt just to be safe to keep the absolute values on every natural log. You just won't see them in the book that way. So anytime the numerator is larger in degree than the denominator, you want to do long division first and then run your integral across the different pieces of it. And also, if you need to brush up on long division, just YouTube A2Grow long division, and there will be a video there for you teaching how to do long division.